All right, howdy folks. Welcome to day 3 of Introduction to Statistics. So in day 1, we learned how to identify descriptive statistics. For example, the mean of a sample, which we call X bar. We learned how to identify the sample size, which we call N, right? That's how many observations that we took from the sample. We learned how to identify the median. Remember that, right? We learned how to identify the range. We also learned how to identify the sample standard deviation, which we call S, and the sample variance, which we call S squared. Okay? So you remember that? Then in day 2, we learned how to create or produce a frequency distribution, and we also learned how to produce a histogram from the frequency distribution. And remember, all the frequency distribution and the histogram told us was if we had a sample of certain observations, let's say 37 heights, the heights of 37 different people, we would simply organize them into categories so that we could make sense of the data. Okay, so that's what we did on day 2. So today what we're going to do is the main thing we're going to do is we are going to learn how to identify inferential statistics or make draw inferential conclusions about a population given a frequency distribution, or how to draw statistical inference from a histogram. This is a very low-level statistical technique, but it's an introductory technique to bring you up to higher levels of inferential statistics, of drawing conclusions. Okay, so we're going to talk about this. So the first thing I want to talk about is how to understand the difference between a sample and a population. Then we're going to talk about what statistical inference is. And then lastly, last couple things here is I'm going to actually show you how to do that in a very simple, basic way with either a histogram or with a frequency distribution. So let's talk about the difference between a sample and a population. And this is a very simple concept here. And it's at the heart of statistics. So what we try to do in statistics is we try to draw conclusions about whole groups of things. For example, in the United States, about 300 million people, and we want to draw a conclusion about all of the people in the United States, and there's 300 million people. So let's say we want to understand the heights of all the people in the United States. If we wanted to understand how many of the people were between 5'7" and 5'11", we could measure all 300 million people. However, it's pretty much impossible to measure all 300 million people. It would take a very long time. It would cost a lot of money to pay people to do this. And even if you had a lot of volunteers to do it, they might not find everybody. And on top of that, by the time you were done measuring everybody, chances are some of the people that you measured at the beginning might have died. And then also there would be new people born because it would take so long. So what we do in statistics is, instead of trying to measure everything in the population, we take a sample of the population. So it might make sense to measure, let's say, I don't know, maybe about 2,000 or 3,000 of the people in the United States, and then draw a conclusion or make an inference about all of the people in the United States, the entire population, based on just the sample that you took. Okay, so basically here's the idea. A population of something, so a population of people, or a population of ants, or a population of, I don't know, a population of chocolates that are made in a factory. Population, well, that's what I call all of them. So when we say population, we're talking about all of them. But the word sample means sample. When we use the word sample, we mean some of them, and usually a much smaller proportion of all of them. So if we want to, for example, we want to determine if there's a chocolate factory where candies are made and you want to make sure that all the little chocolates are delicious, right? Well, you could make sure they're all delicious by eating all of them. But if you eat all of them, then there won't be any left to sell. Therefore, it makes more sense to take a sample of the chocolates, eat those, and then you can infer or assume that the rest of the chocolates that were produced in the same place and at the same time have the same taste, okay? So what we do in statistics is we draw conclusions about populations based on samples, okay? Okay, so what I want to do now is I want to briefly talk about what we call statistical inference. Statistical inference is basically the idea of making an assumption or drawing a conclusion, okay, or making conclusions, all right, so conclusions based on limited mathematical evidence. Conclusions based on limited mathematical or numerical information or evidence. Okay, so inference, the word inference. Inference, okay, so the word inference is based on the word infer. So let's look at the word infer. Now, the word infer is related to the word imply. So, to imply something means you don't actually say it, but you want to communicate an idea to somebody without actually saying it. So, for example, if I say, let's say that yesterday there was a big football game, okay? And it was the only game that was being played. And I say, oh yeah, yesterday I had a hot dog at the game. Now, I didn't say I went to a football game, and there could have been other football games possibly, but if we know that there's only one football game, I have now implied that I went to the football game. And so what another person will do is they might come to me and say, hey, you saw the game, you were at the game yesterday, how did it go? And then I might say, well, I never said I went to the game. And then they said, well, you didn't say it explicitly, but you implied it. You implied that you went to the game. And we do this all the time as people, you know. This is actually what happens a lot of times. This is how our parents, you know, find out what we did without us actually telling them, is they listen to the things we say, they put it together as a puzzle, and then they understand what actually happened, not because you told them what happened, but because they were able to personally put together the facts and the evidence in their head. And without actually knowing what happens, I know this drives young people crazy. My kids go nuts, you know, when I'm able to figure out what they did without them actually telling me what they did. When I do that, when a person puts the evidence together and draws a conclusion about the truth, that's called inferring, okay? So, you know, if I say, hey, I had a hot dog at the game yesterday, I have implied that I went to the football game, and you, hearing what I said, infer. You draw a conclusion based on the evidence that I must have seen the football game and I would know what the score was, okay? So, in statistical inference, what we do is we use statistics like the mean and the standard deviation and other pieces of statistical data. We use statistical data to infer the truth about a population, about what must be true about a population, or what could be true about a population. So that is what statistical inference is, drawing conclusions based on limited mathematical information. Okay, so even though we don't know for sure, we don't know everything about an entire population, if we take a sample of the population, we can get enough information from the sample to draw a conclusion about the entire population through statistical inference. And so now what we're going to do is I'm going to show you how you can use a frequency distribution, which you learned how to create last week or the other day, or a histogram, which you learned how to create, and you can take those devices, you can take those tools, and you can use them to draw conclusions about an entire population, even though you only measured about 45 or 62 of the items from that population, okay? All right, folks, so here's what I'm going to do, is I'm going to explain to you briefly how to infer things, how to draw conclusions about populations using a frequency distribution. So here's what I have. I've created a frequency distribution here, and I'm pretending, I didn't actually gather this data, I made it up, but here's what I'm pretending. But you would do it with real data, okay? So if you were out there in the world doing research, you should not make up any numbers yourself. All of these numbers must come from real life situations if you are a real scientist doing real research out there in the world, okay? So do not make up numbers. I've only made up these numbers for the purposes of education, okay? So let's say that I am trying to understand how long pet dogs live in the United States. I'm just making something up here, okay? So what I've done here is, let's say that I contact 53 random people who have owned dogs. Or let's say it's 53 people. They have had a dog and their dog has died. And so once I gather the data, let's say I tried to get information from like 100 people and only 53 people answered me back. Now that brings up a whole new set of problems, but we're not going to worry about that right now. So I create a frequency distribution, and I title the frequency distribution the lifespan of pet dogs, right? And so I have dogs that may be where their life, they live as long as anywhere from 2 up to 17 years, let's say. And I identify 5 different classes, and each class is 3 years, okay? And so the first class is a dog that lives from 2 years up to 5 years, and let's say of all the people who responded to my survey, 6 of their pet dogs died or only lived somewhere between 2 and 5 years. And then 5 up to 8, and 8 of the people, their pet dog lived between 5 and 8 years. And then 8 up to 11, 13 people had a pet dog that lived between 8 and 11 years. 17 people had a dog that lived between 11 and 14 years, and then 9 people had a pet dog that lived between 14 and 17 years. So that is the frequency of the responses, of the observations, okay, that came in, for a total of 53 responses. So in my relative frequency column, it's a total of 53. 6 out of 53 were 2 up to 5, and that's about 11.3%. 8 out of 53, 15.1%. 13 out of 53, 24.5%. 17 out of 53, 32.1%. And 9 out of 53, 17%. That was 17% of the observations. Okay? Then when we do the cumulative distribution, we're just adding the percentages up and the fractions up as we go. So from 2 up to 5 is 6 out of 53, 11.3%, just like in this column. But this next one, we're going to accumulate the 6 out of 53 with the 8 out of 53. And 6 plus 8 is 14. So from 2 up to 8, when we include 2 classes, the first 2 classes, that's 26.4% of all observations. And that's by adding up 11.3 and 15.1. Okay? So then when we snowball and add on 8 up to 11, it's the first 3 classes, and that's 27 out of 53, which is 50.9%. Then when we add on 11 up to 14, we've now accumulated 4 classes, And that's 44 out of 53, which is 83% of all observations. And then, of course, when we add on the last one, it's all 5 classes, and that's all of the observations. So that's obviously 100%, which is 53 out of 53 observations. So that's here's our distribution. Now, at a very basic level, at a very introductory level, I'm going to teach you 2 basic kinds of questions that we could be asking using this frequency distribution. The first question is a proportion question, and you would say something like, well, what proportion of the population of dogs meets this criteria? The other kind of question is a how many in the population. You could ask, well, how many of all the dogs in the population meet this criteria? And initially, there's basically 3 kinds of questions that you can ask. You can ask either a less than question, meaning less than a number. So you might say, hey, well, what proportion of all dogs live less than 11 years? Or you can ask a between question. You could say, well, what proportion of all dogs pet dogs in the United States live between 5 and 14 years. Or you can ask a more than question. You could say, well, what proportion of all pet dogs in the United States live more than 8 years? Okay? And so we have less than questions, between questions, and more than questions. That's as basic as it gets. Now, when we get to how many in the population, we're asking the same thing. Only this time, instead of asking what proportion, we're asking, well, how many in the population? And so we might say, how many of all the dogs in the United States live fewer than 5 years? Or how many of the dogs in the population live between 2 and 8 years? Or you could ask, well, how many of all the dogs in the United States live, or pet dogs in the United States, the population of pet dogs, how many of them live more than 11 years? Okay? So so really what we have is basically only 6 different kinds of questions at a very basic level of inferential statistics. Okay? So let's do a couple of examples and I'll write them up on the board. Okay, here's our first question. It says, what proportion of pet dogs in the U.S. live less than 11 years? Now, this information over here is only on 53 of the dogs that have lived in the United States. Okay? But remember, we're drawing a conclusion about the entire population. That's inferential statistics, right? Now, are we going to be correct? Are we going to be wrong? We can't know for sure. But there are ways of improving the accuracy of our inference. Okay, so for now, but we're not talking about that right now. For now, we're just learning the basic idea of inferential statistics. So using a frequency distribution, if we're looking for a less than 11 years, what we want to do is we simply want to add up all of the frequencies or the relative frequencies of all the classes that are less than 11 years. And here's what we have. 2 up to 5 is less than. 5 up to 8 is less than, and 8 up to 11 is less than. So really, all we have to do to answer this question is combine these 3 classes into one answer. And that's going to be 6 plus 8 plus 13. Or we can add up the percentages. We can add up 11.3% plus 15.1% plus 24.5%. Okay? And if we did that, what we would come up with is 6 plus 8 plus 13, that's 27 out of 53. Now here's something cool, is that all the less than questions we can actually answer with the cumulative column. Because look, the cumulative column is already adding them up from smallest to largest. So we already have the 27 out of 53, which has already added up the first 3 percentages, and so the answer is 50.9%. Now, proportions can be answered as either percentages or decimals. So you could say that the answer to this is 50.9%, or if you turn it into a decimal, you just move the decimal point over 2 places and you get 0.5 0.509, and we would say P is equal to 0.509. So the proportion of all dogs in the United States that live less than 11 years is about 51% of all the dogs. Okay? Now understand, this is not the truth I'm saying. I made this data up, so you can't, this is not the truth about the lifespan of dogs. You could look this information up, though. You could gather data on the internet on this. Okay? All right, let's try a different kind of question. All right, here's another question. This one is a between question. It's a proportion between question. It says, what proportion of pet dogs in the U.S. live between 8 and 17 years? And so now, to get the answer to this, we want to include all the classes that run between 8 years and 7 years. So we don't want 2 up to 5. We don't want 5 up to 8. We do want to start at 8, 8 up to 11. Well, that's between these. 11 up to 14, and 14 up to 17. So these 3 classes run between 8 and 17. And therefore, what we can do is we can add up the frequencies here. 13 plus 17, that's 30. And 30 plus 9 is 39. We can't make use of the cumulative distribution. But what we could do is we could take, because the last one is down here at 100%, we could take the 100% and subtract away where the cumulative, everything before where the cumulative starts. So we could do 100 minus 26.4%, which would be 73.6%. So remember that number, because I'm going to show you we're going to come up with that same number in a couple other ways. The second way you could do it is you could just come over here to all the relative percentages, the relative proportions, for the 3 classes that we care about, and you can add them up. 24.5%, I have a count, here it is. 24.5%, so I'm going to key in 24.5 plus 32.1%, 32.1 plus 17%. If I add them up, I get 73.6%, which is exactly what I said before when I did 100 minus 26.4. There is a third way to do the exact same thing. You can take, excuse me, you can add up all your frequencies, 13 plus 17 plus 9, so 13 plus 17 plus 9, and then divide that by 53, divided by 53, which gives you 73.6%. So it's 73.6%, or you can say P as a decimal. The proportion is equal to, move the decimal point over 2 places, 0.736. Okay? Now actually in the calculator it says 7358. So if you wanted to write 0.7358, that would also be correct. Because a lot of times our p-values go out to 4 decimal places. Okay? All right, let's try, well, you know what? Let me do another between. Let's say, because I realized that I did the 3 top ones, but what if we did between 8 and 14? Between 8 and 14. You want to try that one now? Go ahead and try it. All right, so now it's only 2 classes. It includes 8 up to 11 and 11 up to 14, but it doesn't include these 2 down here, and it doesn't include this 14 up to 17 up here. And let me show you a clever way to do this. What you can do is go to the cumulative frequency distribution, which is 83%, on the higher one, 83%, and then subtract away the cumulative on the lower one that's not included. So this one says 83. Now go down to this one's not included, 26.4. So now just do 83 minus 26.4%. 83 minus 26.4 would give us 56.6%. Now let's prove that that is the correct answer. So what we can do is we can add up the 2 relative percentages, 24.5 plus 32.1, on the 2 classes that are included. So 24.5 plus 32.1 is 56.6%. Again, the third way we can do it is we can add up the 2 frequencies from the 2 classes that are included, 13 plus 17, and that's 30. and we can divide that by 53, the total number of observations. Divided by 53, and we get 56.6% again. And we could write it as a proportion. P is equal to, move the decimal point over 2 places, so 0.566. And that would be the proportion of pet dogs that live between 8 and 14 years. All right, now let's answer a more than question. What proportion of pet dogs in the U.S. live more than 11 years? And so if we look at our classes, we'll see that 2 up to 5 is not a part of that group, 5 up to 8 is not a part of that group, 8 up to 11 is not a part of that group, but more than 11, 11 to 14 is more than 11, and 14 up to 17 is also more than 11. So to answer this question, we want to use the 11 to 14 and the 14 up to 17. We're going to combine them, okay? And so what we can do is, one way to do it is go to the higher group and go to the cumulative, which is 100%, subtract away the cumulative from the highest group that is not included. So subtract away 50.9%, 100 minus 50.9 is 49.1%. Okay? Now let's make sure that's the right answer by what we can do is we can go over and add up the relative frequency distribution, or relative frequencies. 32.1 plus 17%, 32.1 plus 17 gives us 49.1%. The third way we can do it is we can add up the frequencies, 17 plus 9, that's 26, and divide that by the total number of observations, which is 53. This is the sample size, right? This is n. So 17 plus 9 is 26, divided by 53 is 49. It's actually 4905, but we would round it to 49.1%. So writing it as a proportion, you could write 0.491. You could also write, technically it's 49006. You could also write it as 0.4906. So this is the answer at 3 decimal places, and this is the answer at 4 decimal places. Okay? And that is how you identify the 3 different kinds of proportions. Now we're going to go on to understanding how many in the population. All right, so how do we answer questions about how many in the population? So this question says how many pet dogs in the U.S. live less than 8 years? And the way that we do this is it's a really simple process. We need 2 things, okay? First, step 1 is to find the proportion, which we just learned how to do. Find the proportion. Okay, so basically, we would find the proportion less than 8 years. So we would have to do this first thing first. Secondly, multiply. All you're going to do is multiply the proportion by the population. Okay, so you need to know what the population is. And then find the proportion, then multiply that percentage or that decimal times the population. Well, let's say that in the United States that there are 20 million pet dogs. So let's say capital N, that's capital N means that's the population size. Lowercase n is the sample size, capital N is the population size. So 20 million, and that's a lot of dogs. I don't know what the real number is, okay? I'm not a dog enthusiast, that's okay. I don't have to be, we're just discussing a concept here, okay? But let's say there's 20 million dogs. So if we want to know how many of those 20 million dogs live less than 8 years, remember, we're only approximating here based on a sample, okay? We're not going to be 100% right, but we're going to be close. So we need to know what the proportion is that live less than 8 years. Well, what classes fit in less than 8 years? Well, 2 up to 5 is less than 8 years, and 5 up to 8 is less than 3 years. So we would do 6 plus 8 out of 53, or we would add 11.3% plus 5.1%, Or we could just go to the cumulative distribution, and it's 26.4%. So the proportion is 26.4%. Or we'll say P is equal to 0.264. Okay? And now all we have to do is multiply that number by 20 million. So 0.264 times 20 million, do that in a calculator, is equal to let's see here, 5,280,000. So 5,280,000 dogs. So that's a lot of dogs that live less than 8 years, which is probably a little sad. But again, it's not perfectly the truth. This is made up data, but still, that's how you make the calculation. The answer is, we've answered the question, how many of the dogs in the population are going to live fewer than 8 years? Okay? Let's try a between question. All right, so let's answer the question. It says, how many pet dogs in the U.S. live between 5 and 14 years if the population of dogs in the United States is 20 million? Okay? Well, we're looking for, the first thing we need is the proportion between 5 and 14 years. Well, 2 up to 5 is not included, but 5 up to 8 is, 8 up to 11 is included, and 11 up to 14 is included, but 14 up to 17 not included. So we're just looking at these 3 classes right here. We need the proportion, so we can either add up the frequencies, these 3 frequencies, and divide by 53, or we can take the higher class percentage from the cumulative and subtract the cumulative from the first, or the first class up here that is not included in the group. So included, 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 not included. So subtract that cumulative from this cumulative. So 83% minus 11.3% gives us 71.7%. And if we add it up, 8 plus 13 plus 17, that would be 38 divided by 53, again, 71.7%. Also, we could add up 15.1% plus 24.5% plus 32.1%, and you would get 71.7%. So our proportion, instead of a percent, I'm going to put it as 0.717. And now we're going to multiply that number by the population, and that'll give us our answer. 0.717 times 20 million. Okay, so 0.717 times is 14,340,000. 14,340,000 dogs. Pet dogs in the United States. Okay, so how many of the pet dogs in the U.S. live between 5 and 14 years? About 14,340,000 of them. Again, this is made up information, so this is not actually the correct answer to the question we're asking. You would have to investigate it yourself to find the right answer. Okay? All right, let's answer. We have one more kind of question to answer with this frequency distribution, and that's how many live more than. Okay, so let's answer this question. How many pet dogs in the U.S. live more than 5 years? All right, well, 2 up to 5 is not going to be included. 5 up to 8 is included. 8 up to 11, 11 up to 14, and 14 up to 17, all included. So what we can do is we can take the highest group, which is always included in a more than question, that's 100%, and subtract away the very first group or the very last group moving up that was not included, which is this one. Go over to cumulative, 11.3%. So if we do 100 minus 11.3%, and we get 88.7%. You can also add up the frequencies and divide by 53. You can also add up these 4 percentages, and again, you will get 88.7%. So change it into a decimal, it's 0.887. Now just multiply that proportion times the population, which is 20 million. So 887 times 20 million. And if we multiply those, 0.887 times 21 million is 17,740,000 dogs. And that is how you use a frequency distribution to answer questions about proportion and how many in the population are less than, in between, or more than certain numbers. Okay? Let's now look at how we can answer these same questions with a histogram. All right, folks, what I've done here is I have taken the same information about pet dogs and how long they have lived, okay, and I've turned it into a histogram. So you can see here that my scale is 1 out of 53 because there were a total of 53 observations, that my classes run from 2 to 5, 5 to 8, 8 to 11, 11 to 14, and 14 to 17. And I should put down here, I should put years, because that's my units, years that dogs live. And I could put a title up at the top that says, lifespan of dogs, pet dogs in the U.S. Okay, let me bring this down a little bit. There we go. And so here's my histogram. So with this histogram, I should be able to answer all the same questions. I should be able to answer what proportion of all dogs in the pet dogs in the United States live less than, between, or more than, and how many of the pet dogs in the United States live less than, between, and more than. And it's the same basic process. I'm going to show you how to do a proportion, and then in order to do the how many in a population, again, all you do is identify the proportion and then multiply it by the population. It's just like using a frequency distribution. The reason it's the same is because a histogram is a frequency distribution, but it is a graphical frequency distribution instead of a table. Okay? So let's answer this question. We have what proportion of pet dogs in the U.S. live less than 14 years. Okay, so we're going to go over to the 14, which is right here, and we are interested in all of the blocks that are less than the 14 line. So less than 14 means everything over here, so really we just want to count up all the blocks. Now for convenience, I went ahead and put how many blocks where each column is. So really we have 17 plus 13 plus 8 plus 6. Okay, so that's going to equal 44. So the total number of blocks less than 14 is 44 blocks out of 53. So our answer, what proportion, is going to be 44 out of 53. Okay, so the proportion is 44 out of 53, which we can now calculate in a calculator. 44 divided by 53, and we get 0.8302, which is equal to 0.8302. Notice we don't have any percentages this time. The percentages were only in the frequency distribution, but in a histogram, we typically run in fractions that we turn into decimals. So the answer to this question is 0.8302 of all U.S. dogs live less than 14 years. Okay? All right, let's try a between question. All right, now we got this question. What proportion of pet dogs in the U.S. live between 5 and 11 years? To do between two numbers, we would identify both of those numbers on the histogram, so between 5 and 11. So here's what we care about. We care about this line over to this line right here, and all of the blocks between this line and this line. There's a between 5 and 11. So there's two columns. One column has 8, one column has 13. Add them together, and we get 21 blocks. So that's 21 blocks out of 53, and so the proportion will be 21 divided by 53 is equal to 0.3962. 0.3962. And so that is the proportion of all dogs in the U.S. that live between 5 and 11 years. Let's now do a more than question. Okay, now we're going to ask the question, or we're going to try to answer the question, what proportion of pet dogs in the U.S. live more than 11 years? So a more than question, we only need to identify one line, but instead of going to the left of that line, we're going to go to the right of that line. So more than 11, so we're going to go to the 11 line right here, this line, and we're going to go more than 11. So we want all of the blocks that are on the right side of the 11, above the 11. So that's all these blocks plus these blocks. So that's 17 plus 9. That's a total of 26 blocks. And so that's 26 out of 53 blocks. So the proportion is going to be 26 out of 53, which we can plug in the calculator. 26 divided by 53 is equal to 0.4906. So it's 0.4906. And I want to kind of start getting you used to identifying proportions in terms of 4 decimal places, because that's what you're going to see a lot of, but it's okay to do it to 3 decimal places or to make it a percentage. That's fine, okay? But generally speaking, we're going to identify our proportions. What you're going to see later when we start learning the next thing you're going to learn, you're going to notice that all the proportions are typically given in 4 decimal places, okay? Because they're going to come off of a table. All right, so that's that. Now let's start answering. Let's go ahead and answer some how many questions, okay? All right, so this question says, how many pet dogs in the U.S. live less than 5 years? Okay, so less than means we need to find one line and go to the left of that line. So we're looking for 5 years. Well, here's the 5, so that's what we're looking for. And we want all the blocks to the left of that line right there. Okay, so that's really only 1, 2, 3, 4, 5, 6 blocks out of 53. So we need the proportion. Then we're going to multiply the proportion times the population, which is 20 million pet dogs. So it's going to be 6 out of 53. 6 out of 53 is equal to 0.1132. 0.1132. We're now going to multiply, so that's the P, that's the proportion. 0.1132, we're going to multiply that by 20 million. So 0.1132 times 20 million. Okay. 0.1132 times 20, and we get 2,264,000. 2,264,000 dogs. Okay, how many pet dogs in the U.S. live less than 5 years? 2,264,000 dogs. Okay, remember, made up information. Don't get sad. Okay, I don't know the real numbers. I'm just saying this is how we calculate it. Okay, let's try a between question. All right, so now this question says, how many pet dogs in the U.S. live between 8 and 14 years? And the population is 20 million pet dogs in the U.S. Made up numbers, but this is how you do it. So between 8 and 14, because we have 2 numbers, we need to identify 2 lines. So here's 8, so that's our first line. Let's get rid of this. Here's 14. So we got to do how many blocks between these 2 lines? So it's all these blocks and all these blocks. That's 17 plus 13. It's a total of 30 blocks, right? So our proportion is 30 blocks out of how many? Out of 53 altogether. And you can count up all the blocks and you'll see there's 53 blocks. 53 is equal to, now we're going to use a calculator. 30 divided by 53 is equal to 0.566. And it's 0.5660. So like I said, we go 4 decimal places. But for this one, the 4th decimal place is a 0. So really it's just 0.566. Okay? Now, to find out how many of the 20 million dogs, we have to multiply our proportion times our population. So 0.566 times 20 million. 0.566 times 20 million is 11,320,000. 11,320,000 dogs. And that's our answer. Okay. Only one more example. We're going to answer a how many question, how many more than. All right, so this question says, how many pet dogs in the U.S. live more than 8 years? And the population given is 20 million. So we're going to go to the 8. It's a more than, so we only have to identify one line and then go more than. So that's to the right. So 8 years. Here's the 8. We'll draw a line there. So we want all of the blocks on the right-hand side of 8. So that's this column, and this column. 13 plus 17 is 30, plus 9 is 39. So our proportion is going to be 39 out of 53, which we can do in the calculator. 39 divided by 53 is 0.7358. 0.7358. And then we multiply that number, the proportion, times the population. Okay? So we're going to go 0.7358 times 20 million. Remember, these are made up numbers. I made these numbers up. They're not the truth about dogs in the United States. So we're going to go 0.7358 times 20, 123, 123. But you're not allowed to make up numbers when you are actually a grown-up and professional scientist. All right, so we get 14,716,000. 14,716,000. But while you're practicing as a student, you can make up all the numbers that you want just to practice the techniques. So this means that 14,716,000 dogs, according to this data, live more than 8 years. Okay? So this is how you use inferential statistics using a histogram. And I also showed you how to do it with a frequency distribution. And this is a very, very basic low-level skill, and it should help you to start to learn to understand the basics of statistics. This is an introductory to statistics class, so here are some introductory concepts in statistics. There's a worksheet that you need to complete. I will make sure that you have access to the answers to all the questions on that worksheet. And then also there is a quiz that goes along with day 3. So make sure that you go into the learning system and make sure you take quiz 3. Okay? That's all I have for you today, and I will see you next time in class.